Okay, so I've got in my hand, it looks like this. This is the lecture note for what we did in the last lecture and what we're carrying on with this lecture. So that's on the class webpage. So we started doing some of the rules, and as you can see, there's quite a few of them. But when you get the hang of them, they're all quite natural. I'm going to have a sip now. So we did a few of them. I guess we did a rule like this one, addition. It's too small to see. But you saw we did addition yesterday. Not yesterday, last week. But we've got a few more to go through. And they all have that general format. They tell you exactly what's going on. Alternatively, if you know what's going on, they formalize it precisely. So what we're going to do in today's lecture, about half of it, is do a couple of more of these rules that are particularly interesting. And then we'll get on to something new. Right, okay. So if you remember, we've got judgment forms like so just writing down rules like this, there's some more, which tell us how to reduce, oh, that's a new prime. What happens if we try to evaluate inside a memory sigma an expression E? And when we do all the evaluation, the memory will change. Sorry. And that's not an expression, of course, that's a value. We'll get a result, a value at the end. Whereas if we try and evaluate a command in a memory, we don't get a result. If the command is x equals x plus 1, we'll just get a new memory. So these are the different judgment forms we're going through. So what we did in the last lecture was things like the judgment for evaluating expressions which are pluses and expressions which are minuses, and we also did the rule for do. So there's an expression which is do a command and return an expression, and we wrote down the judgment form for that. It sort of had that form. So now let's look at another command. Actually, before we do that, we have to do something else. Let's look at new again. So I want to write this one. Okay, so we didn't really do new in the last lecture. So let's look at this new. So what it says is, intuitively, not formally, the point about these judgment forms is that it tells you what it is formally, precisely. But intuitively, with a bit of hand waving, it says, well, work out what the result of this is here, and then give x that value. And then, once you've given x that value, carry on. And so we need to evaluate this. So what does that do? Well, we saw the rule for do. It says, well, execute this command and then return x. So if x equals 6, that's fine. We don't need to evaluate 6 anymore. So we'll get x to be 6. And then we'll say, okay, now we have to do x equals x plus 1. X is 6. X equals x plus 1. So x becomes 7. And then we'll return 7. So that's not so hard. Should be straightforward. Should follow that. Now let's do a longer, more complicated one, and I'll try and fit it on the page. New x equals 37 in brackets. New x equals 42 in do x equals x plus 1 to x. Plus x. So this is more complicated because x is being given two values. And then all these different x's, the question is, which x is it? There's two x's here. This x, this x, this x, this x. Which x do they refer to? So to understand that question, you have to understand what's called scope. Scope is a technical term for saying, if you've got various definitions of x, and then you find an x later, which x is it? It's called scope. So, well, the bracketing helps us. So, this x is this x, and this x, well, it'll be the same x, although it's changed its value. So, all of these x's refer to that x. But this x doesn't refer to that x, this x refers to that x. So what we say is the scope of this x is all this stuff here. The scope of this x is, well, it's this x here. It doesn't include this. So that's the thing about the new construct. We put it in because it's technical. But it's important. It occurs whenever you do programming languages which pass variables. So if you write a Java program which has a method which inputs an x, that's like, here's a new x. And then inside the body of that method, you'll do various things to that x. And the x's inside the body refer to the x that's in the definition of the method. That's the scope of that x. So, this x has rubbish. Is there a bin? Whereas this x, this x has scope. So, when you're doing the new constructor, and also when we do lambda calculus, we're going to talk about scope a lot. It occurs in all programming languages because all programming languages define new variables. And all we're talking about is what happens when you define new variables. Now, because of this, we have to be very careful when we do our evaluation rules, because the memory will contain a value for x. But actually, when you're evaluating this, you realize there are two x's. So in fact, the memory has to actually contain a value for all these different x's. And we must be careful. When we do an assignment, and we say x equals 7, so we change the memory so the value of x is 7, we must change the right value of x. You know, if the memory contains 4 different x's, we don't want to change them all. So these rules are set up so that what happens here is that the x that's in scope is the furthest to the right in the memory. So we'll see that in a minute. So, key point. So in the memory, so memories, remember, are so if you get to memory, so that's a list of variables with a list of numbers. Some of those x's could be the same because they'll be arising from this new block where you have many different x's. So, for example, x1 and x3 could be the same variable. In the previous example, as we'll see when we do the evaluation, there were two x's from the two different new blocks. So the memory at some point will contain values for both of those different x's. Okay. So that means some of the x's are the same, so they could be the same variable. So the x that is in scope is the rightmost x. So in order to understand the rules that are coming, that help you do assignment, and that help you work out what new does, you have to remember, in the back of our heads, what's going on is that in this memory, which may have several different occurrences of x, the current x in scope is the rightmost x. You could do it differently, but this is how we're doing it. And this will allow us to make sure that when we do new and when we do assignment, that we change the correct value of x. The correct x. Okay, let's see how that works. So, let's do the assignment rule. Okay, let's get a new pen. So we want to So let's say we've got a memory sigma, and we want to evaluate the command x equals e. So inside the memory sigma, we're going to execute the command x equals e. Now remember, this memory can be built up from lots of new blocks, so there could be lots of different x's. So the question is, which x inside sigma should we change? And we have to work out the value of e first, but then, which x in sigma should we change? Well, I've told you already. The current x in scope is the rightmost x. So at some point we're going to look through sigma and find the rightmost x and change the value of that x to be the value of e. All I'm doing is writing down in formal symbols what this piece of English language says. Okay, so let's do it then. So the first thing, of course, we have to do is quite straightforward. It's what we would have done in the last lecture. First thing we have to do is figure out what is the value of e. So we know how to do that. We can evaluate e. So let's say that we evaluate e. And of course, we have to say, what memory do we evaluate e in? Well, it's a starting memory, it's sigma. And then when we evaluate e, we're going to get a new memory and a value. So let's say the value we get is v. But what is the memory? Well, see, what we want to do is we want to be able to figure out what is the rightmost x. So we've got a bit of notation to explain this. So that's what this is. So let's say the memory we get is we get some variables, and then we get a value of x. So it's a memory. We find a value of x. And then we have some more memory. But I need to say that x is not in here, because I want this to be the rightmost x. I've got to find the rightmost x so I can change the value to be v. So if this is the rightmost x, I need to say that x does not occur in here. Very exciting, I know. How do I do that? Well, fortunately, we're just going to have a pattern. So that's x with a backslash and then sigma. So this means it's a memory. This is a bit of memory, but x does not occur in it. And if you write that, that's what we're saying. You don't have to explain what it means for x not to be in here. You could do that. But all this just says is that when we evaluate e in this memory sigma, we'll get a new memory. and the rightmost x has got the value v prime, and we know it's the rightmost x because x does not occur in sigma prime. So this is a new piece of, if you like, it's meta-syntax. It's a syntax of these rules. It's not the syntax of the programming language, it's the syntax of these rules. And this says x does not occur in sigma prime. So if you read the notes, it's explained, but that's the main point of it. Because we need a mechanism to say, what's the rightmost x? And this is the mechanism to say, this is the rightmost x, because we do it by saying x does not occur in sigma prime. Okay, so now we're almost done. So we evaluate e, we get this memory, and that's the rightmost x. There's some other variables in sigma prime, but it's not x. Okay, and the result of evaluating e, of course, is v. This is the one big memory. You know, it's written out, it's got 3 parts, but it's just a memory. Okay, so then what should we do? Well, what's the answer? We need a memory and we need a value because we're executing an expression. We've got to write a memory, a line, and a value. No, sorry, I got that wrong. This is a command, so we just need to write a memory down here. So what memory is it? Well, it's the memory that we ended up in, except we must change the value of x to contain the value of e, which is v. So I should write sigma 1 doesn't change, but there's my x, whose value is being changed. It was v prime, but actually I now want to set it to the value of e, which is v. And I'm just going to write sigma prime because, I know x doesn't occur in this sigma prime, but it doesn't matter. I'm just giving you the memory at the end. And notice I've not changed the values of any of the variables in sigma prime because I knew they don't contain x, and x is the value I'm changing. So again, it's more detailed. It's part of how we manage memory. Believe me now. The rule for additions, you know, I could say it in words. First evaluate expression 1, then evaluate expression 2. Add the two results together. If you try to write this out in English, it'll be a whole paragraph long. So again, although this is complicated at first sight, what it's doing is intuitively clear, and it's simpler than writing it any other way. And once you've done a few evaluations with this, you'll get the hang of it. Okay, so that's the judgment for assignment. Great. Put that there. Try not to create a mess. So now we can also write down the judgment for new. Okay, so what we want to do is evaluate new. So if you have new, x colon equals e, in C. In prime. Where's it gone? New. Oh, great. I've just found a typo in the lecture notes, so I'll change these on the web page. But now I'm in trouble because now I have to think. I can't look at this. I have to get it right as well. So a new expression has another expression here. This is the pardon? That's an E prime because there are two different expressions. It's new x in some new x equals some expression in another expression. Right, and we have to evaluate this in some memory. So what are we going to get? Yes, that's an E prime. In the lecture notes currently it says C, which is wrong. So I have to get this right. This tells me, this will test if I actually know my material. Okay, so what do we need to do? Well, the first thing we should do intuitively is evaluate this E. Because we have to evaluate the E, change the value of x in sigma naught to be the value of E, and then evaluate E prime. That's intuitively what we must do. But now we must write it out completely precisely in a way that might seem complicated, but actually, because it's tricky, it's best to get it right. So evaluating E in sigma prime, in sigma 0, that is straightforward. So let's evaluate sigma 0, E, let's say that changes to some memory, sigma, and we get a value V. And now we have a memory. So what do we get? Well, just like with assignment, of course, we're going to change the value of x inside sigma 0. And we need to know which x. It'll be the same issue as we had before. It'll be the rightmost x that we should change the value of. So we'll do the same thing we had before. So let's say we get some memory, which is sigma 1, and then an x equals v prime, and then some more memory, sigma 2, which doesn't contain x. So that's exactly the same thing we did in the last rule. It's just to say that this is the rightmost value of x. X does not occur in sigma 2. Okay, so we evaluated E, we get a new memory whose last occurrence of x is this, whose rightmost occurrence is this, and we got a value v. Okay, that's great, and now we should evaluate E prime. So let's evaluate E prime. Let's see if we can fit it in. So we need to evaluate E prime, but what memory should we evaluate it in? Well, no, this is all wrong. I'm very sorry. Dear, oh dear. Right, this is a new x. So you see, this is technical. That's why it's going to be precise. This, of course, is a new x. I can't change the value of an old x because it's supposed to be a new x, isn't it? So this is garbage. And hopefully, some of you are thinking, what is Neil doing? He's writing garbage. He's about to change the value of the old x, when actually he should be creating a new x. So in fact, actually, we're just going to get a new memory. So we'll just get some new memory. But now, we should, when we evaluate E prime, we're going to create a new x. That's why it says new. It won't be any x inside here that we're going to use. It's going to have to be a new one. So we can just stick it at the rightmost end. So actually it should be sigma 1 comma x equals v. So let's get this straight. So we evaluate E, we get a value v in a new memory. And now this value is bound to a new occurrence of x. And you can see I've created a new x. This x wasn't inside sigma 1, well it might have been inside sigma 1, but I don't want to change that value, I want to create a new value. So I've stuck it at the end of the memory and I've got a new x. And now I can do this evaluation. So I'm going to get a sigma 2 and some value v2. So when I evaluate E prime in this extended memory where x has got a new value, I'll get a new value and I'll get a new memory. So overall, I get the value v2. And what memory do I end up in? I need to think or I'll make another mistake. So the x here is scoped inside here. But it doesn't exist anywhere else. It's out of scope. So when I get a memory here, I should not see this x, because the x is only used here. So I'm going to carry on doing other things. I don't want to see this x. So I should get sigma 2, but with the rightmost x gone. So this sigma 2, so I'll write that sigma 3, where sigma 2 equals, so there'll be some more numbers, sigma prime, and then there'll be some value of x, and then there'll be some other stuff where x doesn't occur. And then this should be sigma 3 should equal sigma prime. And then I don't want to have this x because it's out of scope now. I should have sigma double prime. Okay, so I'm sorry I made a mistake. But there you go. Right, so a lot of the exercises will be to get you to use this rule and see how it works. Now, in the rest of the lecture, I want to do a little bit of lambda calculus. So, I know actually there's something else to tell you about. We'll do lambda calculus later. Let's do some Boolean expressions. So I want to evaluate P and P1 and work out the value. So we know the judgment form is inside a memory. If you have a Boolean expression, it evaluates to another memory and a bit. So this is either true or false. So this is the judgment form. Okay, so that's a judgment form for evaluating Boolean expressions. There's a Boolean expression got by the production rule for ampersand. So let's try and evaluate it. So perhaps what we should do is evaluate the first one, evaluate the second one, P1, see if they're both true. If they're both true, then the result is true. Otherwise, the result is false. That sound reasonable? Does that sound reasonable? Yeah? Who thinks it sounds reasonable? Hands, hands, hands. A few. Who thinks it doesn't sound reasonable? How would you, who didn't put the hand up? You didn't put your hand up. How would you evaluate P and P1?
I'm not sure.
If I said, what can I ask you? How would you evaluate some expression plus another expression? Well, we've seen that before. You evaluate the first expression, you evaluate the second expression, combine them. Yeah? So if it's P and P1, is it reasonable to evaluate P and then evaluate P1 and then combine the results? Is it reasonable? Okay. Do you think it seems reasonable? Yeah. Yeah? Okay. Sounds reasonable. So let's write that down. So right. Okay, so we could say, in the first memory, let's evaluate P. And we might get a new memory. And we might get a bit. And then, let's evaluate P1. That's what we said. So in the new memory, let's evaluate P1. So we'll get a new memory, another new memory, and another bit. And then I guess the answer is, well, we'll have sigma 2. And I guess it depends about B1 and B2. So I'll write it in a different color. So this is true if B1 is true, B2 is true, and it's false otherwise. So again, just like we had plus when we did addition, plus on numbers is different from the syntactic plus. This if is not the if in the grammar, in the programming language. This is the sort of meta if, which says, well, if B, we'll look at B1, if it was true, and if B2 is true, then the answer is true. Happy? What do you think? You happy? Yeah. Well, that's possible. It's not wrong. It's not necessarily right. When you're defining programming languages, you define their implementation, there are always choices to be made. It's a very subtle thing to do. That's why it's technical. That's why you need to be completely precise, because the English language will fail to capture the subtleties. So here's an issue with this rule. Let's say P evaluated to B1, which is false. Okay. Well, if P evaluates to false, then we know this should evaluate to false, because false and anything is false. So, should we really evaluate P1? So, what if B1 is false? Question, should we evaluate P1? I mean, you could say the answer should be no, because it's pointless doing all this extra work. You don't need to do that work. You know the answer is going to be false. Doing extra work for no reason is a bit, well, it is pointless. So instead, here's an alternative. I'm not saying either is right or either is wrong. Both are possibilities. Yeah?
So, what is P?
P. P is, we're trying to evaluate P and P1. So it's just some Boolean. It could be, you know, if x is greater than 0, then true, else false. Any complicated expression which is a Boolean. We've got this grammar for Boolean expressions. It's just some Boolean expression. So that's one possibility, this rule here, but here's a better one. Right, so let's try that again. What does this Boolean expression evaluate to? So, let's start and evaluate P. And if this evaluates to memory, and P evaluates to not some arbitrary bit, but let's say it evaluates to false, which here is 0. Right? Then I'm going to stop. I'm not going to do any more because I know the overall answer is false. So, well, I have my new memory, sigma 1, and this should all be false. So that's one rule, which is useful if P evaluates to false, because I know the overall answer is false. But what happens if it's true? So I have a second rule. So if sigma is 0, you evaluate P, and you get a new memory, and you get true. Well, if it's true, then we need to evaluate P1. And of course we should use the memory sigma 1, and we evaluate it. And we'll get a new memory, and it could be something. It could be true or false, so we'll just call it some bit B. Well then, this should evaluate to sigma 2. And if this is true, well, they'll both be true, so we should return true. But if this is false, this will be false, so we should return false, so I can just write B there. Okay, so that's most of what I want to tell you about. The main thing I want to tell you, stepping back a moment, is that there are a lot of these rules now. They're on the web page. You should be able to look through them, and you should be able to understand what's going on. You need to be able to read rules like this and understand what they mean intuitively. If you like, go back to the English language. Read this and say, oh, this says to evaluate P and P1 in the memory sigma 0, evaluate P in the memory sigma 0, and I'll get a new memory, and if I get true, I can carry on. In the new memory, evaluate P1, I'll get another new memory and some B, and that's the overall result, and that's the new memory. So you should be getting, hopefully, the hang of reading these judgment rules, and then writing trees to evaluate overall expressions, big complicated expressions. And then the homework after the current one will be a lot about evaluating these judgment forms, these expressions. Okay, thank you very much. Please remember to hand your 1-minute papers into a box.